Hi, everybody, and welcome back to part two. What we're going to look at and what we're going to try to accomplish for this lecture is to identify sex-linked inheritance. And we're going to look specifically as to how certain traits are going to follow specific chromosomes, either the X or the Y. And we're going to go ahead and identify exactly how to do these Punnett square problems to figure out our genome and phenotype ratios when it comes to our sex-linked inheritance problems. So let's go ahead and get started. One of the very first things is we need to understand exactly what inheritance of sex-linked traits mean and what exactly is that. So when it comes to sex-linked traits, essentially what this means is that they're going to be genes specifically located on our sex chromosomes right here. And remember, when it comes to our sex chromosomes, we're looking at our 23rd pair. So that's going to be XY. So again, when it comes to these traits, they're only going to be found on either the X or the Y. Now, one thing that's going to be important is, as you know, males are going to be XY. And then for females, it's XX. So when it comes to sex linked, there is going to be a really important concept to kind of remember. And one of those big things is homozygous dominant, homozygous recessive, and heterozygous. And the reason why is because when it comes to males, because males only have one X chromosome, when it comes to X-linked genetic disorders, anything like that, they're going to be much more common in males. Again, one of the big reasons why is because when we have a male, we only have one singular X chromosome versus in females, we have 1, 2. So in this case, the example we're going to look at is going to be hemophilia A. When it comes to hemophilia, this is going to be a recessive trait. Okay, so that means that the only way for this to show is that you would need two recessive traits in order for that to manifest itself. The reason why it would be much more common in males is because there's only one X chromosome. So that means whatever they inherit for this one is whatever they're going to show. So in this case, if this was, let's say, a big H, so this person would be exhibiting normal clotting, they would be normal. But if they ended up receiving a little h, because the other one is a Y and it's only following the X chromosome, you can see that they're going to be hemophilic. Versus in females, we have that opportunity to be homozygous dominant, heterozygous, and homozygous recessive, because again, we have two X chromosomes. So if this person, let's say, were to have inherited one recessive gene for hemophilia, as long as they had one dominant, they would not be a person that would have hemophilia. They would rather just be a carrier. So again, in this case, they have the possibilities of HH, H little h, and little h. So in this case, they would have 2 out of the 3 chances of being normal versus just 1, which would be for hemophilic, versus for males, big H, little h, almost a 50-50 shot. So again, hemophilia is going to be sex-linked genetic disorder that is going to be on that F8 gene, and it's going to be specific to the X chromosome. So again, this is our X chromosome. We know this is X because we can see that it's physically larger. Remember, when it comes to X and Y, X is larger, and then Y is about 50% size of our X chromosome. And in this one, we have our F8 gene right here, which is going to code for our factor VIII protein, which is going to cause clotting. So you can see this down here, that if we were to have some sort of damage on our blood vessel, you can see the activated platelets. We're going to form a clot utilizing our fibrins in order to stop that damaged area from evacuating more blood. So let's go and look at an example of hemophilia, which is going to be a sex-linked trait. So again, hemophilia is caused by the mutation of the F8 gene on that specific X chromosome. So that means that it's only following the X. Again, when we're looking at this, it's going to be on the X. It is not going to be on the Y because, again, it's linked or following just that specific X chromosome. So again, without that proper factor VIII proteins, blood of the affected individual will not properly clot. You can see over here that if this was a female, you can see we have XY. This would be healthy, and then this is a male with healthy as well. You can see that is located down here. And that F8 gene, again, is going to allow that factor VIII protein in order to signal and start that clotting. But with a person with hemophilia, for a female, you can see that it would have to be both affected on the XX, because again, when it comes to hemophilia, this is a recessive trait. So in this case, for a female to show, they would have to be homozygous recessive in order to exhibit hemophilia. When it comes to a male, again, remember we have our X and we have our Y. So in this case, whatever they're getting or inheriting from that X is whatever they're going to show. So in this case, they only need one. In this case, the F8 gene, remember, no copying of that F8 gene, meaning that we have problems with our factor VIII protein, meaning that we are no longer going to be able to signal, again, that clotting, so blood is not going to clot. So this is what that's going to look like. When it comes to sex-linked, there's going to be two things that we need to track when we're doing these sex-linked problems. The first is going to be the sex chromosome, so we can identify whether they're going to be male or female. And then we need to go ahead and write a superscript in order to identify whether they're going to have, let's say, normal blood clotting, or if they're going to have hemophilia A. So looking at this over here, remember hemophilia A is a trait, and normal is going to be dominant. So in this case, we have big H, which is going to give us a dominant trait, meaning that they're going to be a normal person. When it comes to hemophilia, again, that's going to be a recessive trait, so that's going to be a little h. So again, since the F8 gene is present on the X chromosome and it's linked, this is how we're going to write it. You can see to represent normal, whenever we have an X, it's going to be our X, and then our superscript, which is little h, I'm sorry, big H, which is going to denote a normal person. When it comes to hemophilia, again, it's X-linked, so it's only following the X chromosome, and then we would have a little h. Okay, so looking at this is how you would write this. Remember, when it comes to a female, these are going to be all the genotypic possibilities. Again, they can be homozygous dominant. You can see, remember, it's X-linked, so it's only following that X sex chromosome. And then again, we need to denote whether they're going to be dominant recessive. So in this case, X big H, X big H. So in this case, this would be a homozygous dominant female for normal blood typing. For this one over here, you can see that we have a X and then an H. Again, that's how we write that here. And then X and little h. So in this case, this person would be a carrier right here. And then finally over here, the only way for them to show hemophilia is it would have to be homozygous recessive for that trait. So again, that means they need to have two little h's in order to show hemophilia. So again, these are the genotypes. We would have XX representing a normal or representing a female, and then we have our big H representing our normal. So in this case, it'd be normal female. For this one, we have XX again representing it's a female, and then we have a big H little h representing heterozygous. So in this case, the phenotype physically, this is going to be a normal female, but they are going to be a carrier because again, they do have that recessive trait that they can pass along. And then finally, for this one, you can see we have XX, which again is going to denote a female. And then on our superscripts over here, we have little h, representing that this person is going to be homozygous recessive, meaning they are going to have hemophilia. But again, you can see this is going to be much more rare in females because they have two opportunities right here to not exhibit or have hemophilia. Unlike males, you can see that in our genotypes right here, we would have XY. So we're writing XY to represent a male. And again, it's only showing up on the X chromosome. So again, right here, superscript big H. And it is not showing up on the Y. We're not writing anything here because again, it is not Y-linked, it's X-linked, meaning it's specifically going to be found on the X chromosome. And then over here, this is going to be our recessive trait. So again, you can see that we have our X and our Y written here, XY representing a male. And then again, you can see we have a superscript with an H. So in this case, this person is going to have hemophilia. So again, the reason why we don't have a heterozygous or we don't have a carrier is because males only have one X chromosome. So that means that this option here that is present for females is not present for males. So again, our phenotypes are either going to be yes, they have it, or no, they do not have it. All right, so let's go ahead and test our knowledge and see exactly how we can do some of these problems and how we can fill out this Punnett square along with identifying and filling out a pedigree. So looking at this over here, it says Jane's dad, John, has hemophilia A. Okay, so it's going to be an X-linked trait, and Jane and her husband Joe want to have children, but worry about having a child who has hemophilia. They consult a genetic counselor who illustrates Jane's family history and inheritance of hemophilia. So what we're going to do is we're going to go and fill out our pedigree first. So we know that John, right, Jane's dad, John, has hemophilia. So we know John is Jane's dad, so we know that's going to be XY, and we know that it's X-linked, so that means it's only showing up on the X, and we know that they have hemophilia, so that means that it's going to be a little h, because remember, hemophilia, if it's going to be a big H, they're going to be normal, and then if they have a little h, they're going to have hemophilia. So in this case right here, we know John, who's shaded, has hemophilia. So John's a male, XY, and then they have hemophilia, so they have a little h up top. Okay. So we're going to go ahead and go on. I'm just going to go ahead and have those all filled out for you. We were able to grab all of this from our reading here. So again, Jenny is a female, so XX, and then they're going to be homozygous dominant for normal blood. And then Joe, again, does not have hemophilia. So in this case, XHY. And then Jane is not going to have hemophilia, but is going to be a carrier. So in this case, they're going to go ahead and cross everything, do a Punnett square cross. So again, we have Jane up here, female, XX, and then this person is going to be a carrier, so I have big H, little h. And then Joe, it's a male, so again, X and Y, but it's X-linked, so it's only going to have a big H on one of them. And then what we're going to do is we're going to try to figure out the probability of a male child who would have hemophilia A, and then a female child who would have hemophilia A as well. So we're going to go ahead and do this cross. Again, the way that we're going to do this is we're going to go ahead and take this right here, and we're going to drop it down here and here. So when we're dropping these down, this is all moving down as a unit together. So we have X and X here, and then our H right here and right here. Remember, superscript. Same thing with this, bringing this down here. So we have X, big H, oops, I'm sorry, X little h. Let me go ahead and fix that quickly. So then I'm going to actually put this over here, because the littles are usually in the back. And then X goes first, sorry. And then go. Okay, and then we're going to go ahead and take these and drop these off here. So we have X, big H, X, big H, and then we're going to take these and drop these off here. So Y and Y. So looking at this over here, you can see that we have our males, which are going to be located down here in this highlighted portion here, and our females are going to be up there. So what we need to do now is we need to identify male, so the probability of them having hemophilia A. So looking at this, we can see that we have an XY, so this is our male, and then we can see that on our X linked, we have a big H, so that means that they are not going to have hemophilia. But you can see this one does, so we have about a 50% probability for males to have hemophilia A. When it comes to a female child with hemophilia A, we're going to look at this. We have this. So these are going to be our females. You can see HH. So this is homozygous dominant. H little h. This is going to be heterozygous. Again, H is dominant. So you can see that. So in this case, they would not have a probability of a hemophilic female. So that's what this should look like. And then this is what that Punnett square should look like at the end. Okay, so we're going to go ahead and do one more. So what I'm going to do is I'm going to have the question showing, and then I'm going to give everybody an opportunity to go ahead and pause this, give this a try, and then we'll go ahead and check it out as a class. Oops, there we go. All right, so let's go ahead and check this out together. So it says Kevin has hemophilia A right here. So I'm going to, actually, you know what? I'm going to go ahead and highlight this. Highlight all of our important information. So we know Kevin has hemophilia A, and we know that it's an X-linked trait. Kate has no history of hemophilia. So we know Kate here has no history of hemophilia. Kevin and his spouse, Kate, want to have a child, but worry about having a child who has hemophilia. They consult the genetic counselor, hemophilia. So we're going to go ahead and do this problem. So we know Kate right here is homozygous dominant for normal blood. And we know Kevin has hemophilia. So we know Kevin's a male, so we know it's going to be XY. And we know that it's X-linked, so that means it's only following this X. We know that, again, big H is for normal, little h is for hemophilia. So we'll put a little h superscript right there for Kevin. So then we're going to go and write this down. So we know Kevin has an X, little h, and then we know he has a Y. Kate is X, big H, X, big H. Okay, so now what we need to do is we need to answer these following questions. What is the probability of a male child who would have hemophilia A? What is the probability of a female child would have hemophilia A? And then what is the probability that a female child would have heterozygous carrier for hemophilia A? So this one, we want to know if they're going to have hemophilia A. This one, we want to know if they're going to have hemophilia A as well. Remember, it's going to be female child, and this one is going to be a male child. And this one, we're trying to figure out a female child for carriers. So let's go ahead and do this. What I'm going to do is I'm going to cross these down and do the X's and Y's. So this would be X, 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 X. This one is going to be X, Y. And then this one over here, X, and then Y. And then we're going to go ahead and do the H's now. So H here, H here, here, and then here, big H here, and then big H here. Okay, so now after we've done that, we're going to go ahead and check this out together and see exactly what the probability of the male is going to be. So looking at this over here, we can see that this highlighted portion is going to be our males. And looking at this, you can see that we have X big H, X big H. So what's the probability of a male child that would have hemophilia? In this case, it would be a 0% if Kate was homozygous dominant and then Kevin was positive for hemophilia. In this case, for female, how many of them are going to have hemophilia A? Looking at this over here, you can see that we have our females here, and we have dominant, dominant. So no, we have a 0% chance as well. What is the probability of that a female child would be heterozygous for hemophilia A? Remember, heterozygous is going to be different. So in this case, we have a big H, little h, so they're both different. So we have about a 100% chance of them having a carrier. So that's what that should have looked like. All right, and that is going to conclude part 2. As always, if anybody has any questions, comments, concerns, please feel free to reach out. I'd be more than happy to answer any questions you have, and I look forward to seeing everybody in part 3.